pure gain value without a phase. Right? So if you need a controller to provide some additional phase to your system at certain intervals of frequencies, okay, what can you use? Obviously, you cannot use K, right? K is just A. You cannot provide phase. And you know that if you will add phase or remove phase, you are going to place your closed loop poles differently. Okay? Which will result in different behavior for a closed loop system. If you remember what you see on your microscope. Alright? Okay, so for those who still don't quite understand what I'm saying, let me just draw you something, right? I'm not good at drawing, but I think I'm better at drawing than explaining stuff. Okay? Imaginary rail. Yeah? That's Nyquist plot. Nyquist plot is a plot of closed loop locations. Okay? You will be able to find out what the closed loop location in a way as omega stands from minus infinity. Right? You know something about the closed loop location because you know something about stability. Alright, but what is it that you plot? What you plot is J omega, which is your open loop transfer function. Okay? So by plotting J omega, which is an open loop transfer function for omega from minus infinity to infinity, you know something about stability. Because of the Nyquist stability criterion. And from that, you know something about the closed loop pole location, because you know something about the behavior. Alright? So that's the strength of using a Nyquist plot by plotting J omega. You can tell about the stability of the system and also how the closed loop poles will behave. Okay? So if this is your J omega, alright, we know that from Nyquist stability criterion, the critical point is here, -1 plus J0. Okay? And you know that the further away you are from -1, the more stable you will be. Yeah? Correct? And since we know that -1 is the stability point, you're going to extend a unit circle, radius of 1. Okay? You know that at this point, there's a certain phase, which is negative. Alright? And you know that you can shift this point closer or further away from -1 by adding more or less phase. Okay? And why would you want to shift this point upwards? To be nearer to -1. So that you have a capacitor system. Okay, if you imagine that you are going to have second order poles, the nearer you are to -1, the faster is your response, although you have more oscillations. But in some instances, maybe you need this quick response. Alright? Okay? Alright, what's more important about Nyquist plot is for you, first of all, to be able to draw what is J omega in terms of gain and phase for different frequency range. And also to be able to tell the stability criteria, what's your gain margin, what's your phase margin. So this is lambda, A for gain margin is 1 over lambda. This theta, your phase margin is 118 plus theta, which is negative. Okay, so if you want to add phase or minus phase, pure K will not do, because of pure K, all it does is just simplify yeah. Okay, so once you have magnified the point by a certain amount of K, you may want to shift this point slightly away. Yeah, to add some phase margin. Yeah, so the system becomes more stable. Okay? You might want to have a big gain, so that you have a smaller steady state error. But you might want to move this point further away from this -1 point. Okay, so you want to actually introduce more phase margin. Alright, if you want to introduce more phase or you want to reduce the phase margin, you need additional terms in your controller. And what are these terms? These terms are either lead terms. LEAD, lead means you have more zeros, because zeros have positive phase in your system. Or they can be lag terms. Okay, lag terms will be more on the poles, because lag terms will take away phase from the system. Alright? Okay, so a bit of explanation for you to understand what is it that we're trying to do here. Okay? So, a definition of lead compensator, as such, CS means controller. 1 plus S over omega C over 1 plus S over alpha omega C. Okay, and we tell you that alpha is a high frequency name. Alright? So in this system, you can see that you have got more from the zero in terms of phase than you get from the pole. Alright? And your phase angle is always positive. Okay? Why? For those who still cannot get around to this, what's the phase of this controller? Angle of CS. Alright? Will be positive tangent inverse. What you get from the zeros? Because zeros give you positive phase. So if S is J omega, then omega over omega C. Right? Minus tangent inverse omega over alpha omega C. Okay? Punch into your calculator, you will see that this is always bigger than 0. Alright? All you need to do is assume some values, punch it into your calculator. Okay? So in this format, the phase angle is always positive. Alright, you can have different omega C, different quantum frequencies. Okay? But the phase angle always positive. Okay? Yeah, it's written over here, right? Okay, if you look at this simplification, some of you may ask me, do I need to know that this is this? I'll think that you should. Okay? Any of those equations involving combination of tangent inverse or alright? So you have quite a bit of all this set in your notes. Okay, so please make sure you know that. Because you might require that for solving frequencies with the phase angle criteria. Okay? I will say that the phase angle is maximum when 1 plus omega squared over alpha omega squared, which is on the denominator, is what you have. Okay? My numerator and okay, what I do is this is the phase angle. So you want to find maximum phase angle. So this phase angle is set with this 5 over the omega. Okay, which is 0. Find the turning point of phase angle. Alright? So this is to find the turning point, like how I identify the turning point on the curve. Okay? And you can simplify that this is this. Alright? How well do you need to know this? I think this has not been tested before from RCF machines. Yeah? So please just go through it to understand how you work from the so I've explained earlier on that if you were to add phase to the system, meaning moving in nearer to -1, what it's going to do is it's going to be no more oscillatory, right? So it also means that the response will be faster, right? Okay? So the purpose of the lead compensator is to improve the high frequency response, okay, of the system. Alright? Okay, if you move on to lag compensator. Alright, for lag compensator, meaning we add negative phase to the system. So instead of the alpha on the denominator, alpha is on the numerator. Alright? Make the same analysis. Okay, for phase angle. The phase angle is always negative. Alright, all you do is just substitute some value. Okay, same here, find the center point, identify the exponential. Alright, now why do we use a lag compensator? To improve the low frequency. Okay, you can also combine these two because you might want to introduce more phase at certain frequencies and less phase at certain frequencies. Okay, so you can do this with lag compensator. Alright? Which is can be something like this, or it can be more. So you can have more terms depending on what frequencies and how many frequencies you want to introduce phase or phase. Okay? So if you remember from a body plot, when you have multiple terms, all you need to do is to take into consideration the phase of each of these terms. Right? It's called a phase plot. Alright? Okay, so another method is just introducing more phase or less phase at certain frequencies, which will affect the behavior of the system. Alright? So if you state this like this, omega 1, omega 2, omega 3, omega 4, where omega 4 is much bigger than omega 3, much bigger than omega 2, much bigger than omega 1. Alright, you will notice that what happens in this configuration, with this assumption that omega 4 bigger than omega 3, bigger than omega 2, bigger than omega 1, then your phase will first goes negative and then positive. Alright, all you need to do is spread out the phase equation. See that. Okay? Alright, just understand how it works. Alright? Okay, so you're going to look at a tutorial. Okay, you'll realize that question 1 to 9 is on general control concepts. Question 10 to 12 is on the root per weeks. Question 13 to 19, the root locus. 20 to 32, the Nyquist plot. Okay, so what is it that you need to know? For dynamics and control, the controls portion, you need to know this, and this. Okay? Need to. Okay, meaning you must know this. Okay? Alright? So what are some of the tricky things that you can expect to see will be, for control, general control concepts. Please make sure you know all your theorems. Please make sure you know all your definitions. Okay? And make sure you know what it means by poles, what it means by zeros, what is the dominant pole, and what's the behavior you expect to see when you have poles at certain location. Alright, we'll go through a little bit about that later. Okay? For root per weeks, stability criterion, what do you need to know? You need to know the 3 rules. For first and second order system, okay, for third order systems, and highest order systems. Alright? Based on the 3 rules, be able to tell the range of K for which the closed system is stable, okay, by identifying the characteristic. Alright, we have gone through some. Also, what can be tricky here? We can give you coefficients for a characteristic equation, and some coefficients are not there. So at one look, all you need to tell us is not stable for any value of it. Okay, so there are some tricky questions that we can set from there. Alright? And in addition, for higher order systems, if you ever see a question for higher order systems, make sure you know how to create a root for its infinity array. Okay, for higher order. Root locus, we have gone through quite a number of questions on root locus, is plotting of floating poles. As k tends from minus infinity to infinity. Alright? So what are some of the tricky things? You have to know step 0 to root 8. So altogether there are 9 steps. Step 0 is just listing how many poles and how many zeros. Okay, then you talk about if you have more poles than zeros. Okay, you know that the open loop poles have to have the open loop zeros. Okay, because of the gain calibration equation. Alright, total zeros and position that k is infinity. Alright, so there are some open loop poles. Okay? Alright? And if n is bigger than n, there are some open loop zeros that have nowhere to go to. Okay? Alright, so with this, you know that there are n minus n asymptote, meaning the trend line, curve, or whatsoever, that the remaining open loop poles can follow as k has to be infinity. Okay? So you need to find out the center of asymptote. Okay, and the angle of the asymptotes. Okay, and after that, see if we can calculate the number points. Number points is just EG over ds equals to 0. So what can be tricky here is you must make sure you know your partial fraction, because we need to do a partial differentiation of the transfer function. Okay, so that is u prime square. All right, and next, if you have a double point here, and you know that the asymptotes are such and crossover, you will be expected to find what is the point of stability. Okay, so for this, you can choose to use the root over stability criterion to tell me what is this k value. From this k value, tell me what is omega. Okay, or you can use your phase criterion to tell me that this is the point whereby I have 0 real parts, it's all imaginary, okay, and solve omega. Okay, and etc. So there are a few criteria to use. I'm just running through the steps, so don't even have to take down this, okay? Because we'll do a revision later. Alright, Nyquist plot, as I say, it's just plotting on A magnitude. So once again, for Nyquist plot, please make sure that you follow this. Okay, given a transfer function, be able to write the magnitude condition and the phase condition. Okay, first thing you need to do, draw me a table, 3 columns, omega values, the magnitude, and the phase. Alright, so we're going through a few questions. Make sure you know how to use your own calculator. Okay, if your calculator spoils, make sure before the exam, this other calculator that you're going to use, you know how to use it. Alright? So one thing you earlier do for yourself is make sure that your calculator has got sufficient battery to last you. I think your exam is the 20th of May for 9th. It's still provisional, so it's going to be almost the end of the exam period. Alright, so make sure your calculator has sufficient battery power. Okay? Alright? Okay, so 11:28. This is what I'm going to do. I think we should continue and we end early. Alright, we'll continue with one revision question. We'll take a break and see where we'll do more. And if possible, we'll end. Okay, so I said I've selected some revision questions so that you can cover a bit more on the general principal concepts. Okay, August 2012, question 5. Okay, so what I'm going to propose here is that we spend about half an hour, which will be 12 o'clock then, we'll do this question. Alright? For those of you who feel that you will not be able to derive value from doing this, you are free to go. I will stop you. It's fine because we have covered our lecture anyway. Okay? So we spend half an hour on this and then we'll go through the solutions. Okay? We'll take a quick break and possibly we'll do one more question on co-location and behavior. Okay, so just to run through why do I cover this question and how did I select this question. Alright, as I said, you must know your definition because the beginning of every single question will often be a definition. And it's not enough knowing what is gain, margin, base margin, what is anchor criterion. You also have to know things like what is the class final value theorem, how to write it down. Okay? So simple things like stating this, stating criterion for a other system, and explain what is meant by dominant poles of the system. Alright, so these are things that I expect you to know, but they are not very explicitly defined in the lecture notes. Okay? So this is very much about how much you understand the material in the lecture. Alright? D, straightforward. Anything that's about the group calculation is very straightforward, okay? D, straightforward. E, find the statistic error, so this relates to part A. Okay? Because if you can state the final value theorem, you know the final value of the output. And then you will know the statistic error. F, how do you relate your characteristic equation in terms of position of dominant poles to the behavior of the system? In terms of the damping and the frequency of oscillation. Alright, so try this for half an hour and we'll review the answers at 12 o'clock. Okay, meanwhile, if you want to go, feel free, if you want to stay, feel free. Alright? This is our choice. Okay?